All right, welcome. In this video, we're going to introduce pressure and think about some variables that impact each other in pressure when we're thinking about gases. And so pressure is the force per area. And the way that a sample of gas exerts pressure is those little gas particles, maybe they're molecules, maybe they're atoms, they're moving around constantly and they're bouncing off of surfaces. And it's important to keep in mind as you're thinking about variables that impact pressure is that something that would increase the number of collisions per area would increase the pressure. So the more collisions you have per area, the more pressure you have. And gases are exerting pressure on you right now. We're used to it. We don't feel it really, but there's gases all around you. They're pushing on you every different direction. And there's different units we can use to measure pressure. Some of them are over here. We will often use either pascals or atmospheres. And to get a sense of what is an atmosphere, the air pressure, in your room right now is about 1 atmosphere, because that's about the air pressure at sea level. It can vary a little bit, but it's about 1. And there's some different variables that will affect pressure, like the number of gas particles, the temperature of your gas sample, and the volume. And so what we're going to do is we're going to use some simulations in Odyssey to observe these relationships between these gas variables. And so this page right here has some directions to kind of show you how to get to various things. And then we have some slides in here for you to take data. And so you should be, recording this in your OneNote, in your notes, play around with the demo, write down some data points. I will show the demo here in case you're having issues with Odyssey. But if you can see Odyssey on your own, then you can just pause the video right now and go do this on your own. But if you need to see these demonstrations, I will pull them up. So the first one is concept. So this pressure-volume relationship. If you look here under, let's see, miscellaneous, under gases, this first one, G1, this is collision theory and Boyle's law. Okay, so it looks like this. And what we do is we hit play and we can see these gas molecules bumping around. If we want to, we can click show, and this will show every time a particle collides with the wall. And that's important because that's what causes pressure, is those collisions, right? So that's kind of useful. And you notice how there's a toggle here. So what we can do is we can decrease the volume. And now look at that. We see a lot more of these green things lighting up. So we have a lot more collisions happening. And we can look at the pressure here. There's 2 places we can read the pressure, up here or right below it. So at a volume of 406, let's go back to our, at a volume of 406, the pressure was about, was it 10.06 atmospheres? I think it was. And then if we go back to right here, if we increase the volume up here to 8,125, this is nanometers cubed is what our measurement here is, we see we have much fewer collisions and the pressure is 0.5 atmospheres here. So what we want to notice is that when you increase the volume, the pressure decreased. And that is because the number of collisions decreased. That is our takeaway from this demonstration. And then we want to think about it mathematically. So this relationship, as pressure increases, the volume decreases. That looks like an inverse relationship. So we want to figure out which of these mathematical equations best fits this relationship. Is pressure times volume constant, or is pressure divided by volume constant? And if you're not trying to figure this out, we can pick 2 sets of data points. Let's actually do this so we can kind of see what we're talking about here. If you're like, what does she mean here? Let's try this out. So if we take pressure divided by volume, so pressure divided by volume, that certainly does not look constant, but let's maybe plug this in so we can check it. So 10 divided by 406 is 0.024. 0.5 divided by 8152 is a lot smaller, 0.00006. Okay, so that's definitely not equal to each other. So pressure divided by volume does not seem to be constant. pressure times volume. Let's see about that. So what if we do 10 times 400 versus 0.4 times 8,000? I'm just kind of rounding here. So 10 times 400 is about, 4,000, and then 0.4 times 8152, I'll round 8152, is about like 3,260. So that's pretty close. So it seems like pressure times volume is staying relatively constant here. Pressure divided by volume is definitely not constant. So this is our relationship here. We have an inverse relationship. As this one goes up, this one goes down. That means pressure times volume is constant. Cool. Okay. Inverse. All right, let's take a look at another one. Pressure temperature relationships. Let's go back to this demo. And again, I'm just showing this if you are having issues with Odyssey. Of course, if you are having issues with Odyssey, I want you to seek out some tech help here. But what we're looking for here, because you might be able to do this on your own, but in miscellaneous, scroll down here to gases, and we're looking at this one, G2. And let's hit go here, and we can see we've got a temperature and a pressure. So at a temperature, let's go look back at our data set here. So temperature 25 degrees, the pressure is 1 atmosphere. So 25 degrees, it's 1 atmosphere. And then we just want to pick 2 other temperatures. You can pick whatever temperatures you would like. So I'm going to go, let's go higher. It looks like if the temperature is around 230, the pressure is around 1.7. So the temperature is 230. This is around 1.7. And then let's do one more. Let's go extreme here. What if the temperature is 659, the pressure is 3.1? So 659 is 3.1. And what we should see here, so we increase the temperature, the pressure is increasing. And that's because the number of collisions increases. So let's take a look at that. I didn't really focus on that in the picture. Notice at these really high temperatures, the molecules are moving around faster, so they're bumping into the walls more frequently. If you lower the temperature, the molecules move a lot slower, so they're not colliding as often, and that is why the pressure is lower. Okay, so this looks like a direct relationship, and you can figure this out. You can kind of test this theory out by taking the pressure, divide by the temperature, and make sure it's still constant. Turns out this relationship only works when you are doing your temperatures in Kelvin. Okay, so because if you take a look at this here, you might say, gosh, the temperature is 10 times higher, but the pressure is not 10 times higher. But the reason why is because you have to look at your Kelvin temperature. So to find the Kelvin temperature, use a different color here, you're going to add 273 to everything here. So your, and then let's see how our math works here. So this is 298 Kelvin, and this is 503 Kelvin. And it seems to be a direct relationship, so I would expect that the pressure divided by temperature should be constant. So let's check that out. So if the pressure is 1 divided by 298, versus over here, this is 1.7 divided by 503. Let's kind of check the math here. 1 divided by 298 is like 0.00335, and then 1.7 divided by 503 is about 0.00337. Cool. So that seems to be constant. So pressure divided by temperature is constant as long as your temperature is being measured in Kelvin. That is super important when we get into gas law calculations. And the reason why this is important is because the Kelvin temperature is directly proportional to your kinetic energy, to the speed that your molecules are moving. So 0 Kelvin means they're not moving at all. So we need to use Kelvin temperatures. All right, and the last one, the volume moles relationship. This is the Avogadro's one. If you can't find it, let me show you how you can find it here because it's not in this menu. You have to go to a different menu here under demonstrations, I think. But what I did is I just searched it. It is, because I couldn't find it in this version. Avogadro's Law. There you go. So there's a little search button, which is cool. Good to be aware of. Let's pop this up. And so what Avogadro's Law tells us is the relationship between particles and volume. So we're going to write down some data sets. In this example, we've got 75 molecules, and the volume is, where's our volume? Oh, here it is. So 75 particles, the volume is 661. So we have 75 particles, the volume is 661. I can't remember what the units are there. Let's go back here. If we go up to 135 particles, the volume is 8.8. So 135 is, wait, not 8.8, I think it's 881. Sorry, I'm looking at the wrong thing. Here it is. Here's the volume. 1,189. Okay, 1,189. 1,000. Okay, and then let's do one last data set here. Let's go to extra small. So if you have 45 particles, it's 396. So 45 particles, the volume is 396. So notice if you increase the number of moles, the volume increases. So this seems to be a direct relationship. And actually what's cool is if you look back at this demonstration, it actually shows you, it just actually calculated this ratio, volume divided by n. Let me show you where that is. So right here, volume divided by n is 8.8. So notice that no matter what our number of particles is, you see how this stays constant? So as I shift the number of particles, the particles change, the volume changes, but the ratio of volume to particles is remaining constant. Cool. So that's our goal, is to see what these three different relationships are. And now what we're going to do is if we put them all together, we know that pressure times volume is constant. So that's an inverse relationship. Pressure divided by temperature is constant. That's a direct relationship. Volume divided by moles is constant. We saw that one. This one we did not see a demo of. There wasn't a good demo showing pressure moles, but it might make sense that as you add more particles, you're going to have more collisions, so the pressure is going to increase. So there's also a direct relationship between pressure and moles. And so what we can do is we can combine all of these together into one relationship, and that's pressure times volume divided by temperature times number of moles is a constant. And this is what leads us to what we call the ideal gas law. So the ideal gas law is just this right here. Pressure times volume divided by temperature times moles is a constant. And then we label this constant R. So if you look on your equation sheet, you'll see R. It's a constant. It's just a letter we picked to represent that constant. And so PV divided by Tn is equal to R. Most often you see it written this way. PV equals nRT. So pressure times volume equals the moles times the gas constant times temperature. And this is what we will be using next, is the ideal gas law. All right, thanks for watching.